Welcome back to Geometry, Chapter 3, Section 5, using properties of parallel lines. So, remember, parallel lines are like the rails of a railroadway train track that should never cross. They're always stay the same distance apart. So, we're going to do a proof to start with this. The proof says lines M, N, and K represent the three oars of a rowing team. M is parallel to N and N is parallel to K. Prove that M is parallel to K. Okay? So first we tell our givens, and it was that M is parallel to N and N is parallel to K. And notice that if you're looking at the book, I'm doing it in slightly different order. I like to put all my givens right up there at the front. I don't like splitting them up. It's not wrong, it's just different. There's lots of ways to be wrong, but there's more than one way to be right with this. Okay? The next thing is we said that angle 1 is congruent to angle 2 by the corresponding angles postulate. See how they're in the same place? If this is the transversal hit crossing those lines, those are in the same place. And then angle 2 is congruent to angle 3, same reason, they're in that same place. Then we can say 1 is congruent to 3. Do you remember why? The transitive property. If A equals B and B equals C, then A equals C. Remember that? It's so important we have a hand signal for it. So this is the transitive property. And sometimes we just say transitive property, sometimes we'll say transitive property of angle congruence. You can add that on there. Therefore, we can say that line M is parallel to line N. We've proven it by the corresponding angles converse. Because the angles are the same, we know that these lines are all parallel. All of the lines are parallel there. Yeah, and that, I wrote that one wrong down. It should be, yes, it's parallel to N, but it's parallel to K is what we were supposed to be proving. We were already given that it was parallel to N. Alright, so there's the proof. That's a good one. I would expect you to be getting close to learning how to do this. Okay, here's another proof. Here, this is a lovely drawing of a step ladder. It's got 3 steps in the top, and we're given that this line going through the top is parallel to the second step, to the third step, to the floor, and those are given. And we're supposed to say that therefore we know that the top step is parallel to the floor. And how we can say that is the transitive property. So the transitive property can be more than 3. It could be if A equals B and B equals C and C equals D, then A equals D. It could have more, is the point. They wrote it as a proof. Look in your book, you can see the theorems. I meant to write those up there, but I forgot. Okay, theorem 3.11. If two lines are parallel to the same line, then they are parallel to each other. That's what we just did with this one. And in a plane, if 2 lines are perpendicular to the same line, which we're going to see here, then they are perpendicular to each other. Let me draw that. Okay, so you got this line is perpendicular, and this line, imagine this line right there, is perpendicular, and they're both perpendicular to the same line, then we know these two are parallel to each other, right? So this, I'm going to tell you this one, I'm going to read it to you as a paragraph proof. You are given that K1 is parallel to K2, and K2 is parallel to K3. By the transitive property of parallel lines, K1 is parallel to K3. Since K1 is parallel to K3 and K3 is parallel to K4, it follows that K1 is parallel to K4, so the top step is parallel to the floor. So that's a paragraph proof. No, my favorite is too wordy. I like the 2 columns, easy to see, not so many words. Okay, we're going to do another proof, and this one has to do with bookshelves. And we're going to do it as a flow proof. Okay, so let me read to you the situation. You're building a CD rack. Here's the little shelf. Whoop, what a great drawing. You cut the sides, bottoms, and tops so each corner is composed of two 45-degree angles. Prove that the top and bottom front edges of the CD rack are parallel. So there's my cuts. Each of these are 45. And this is corner A, B, C, D. Alright, so as a flow proof, we're given the measure of angle 1 is 45 and 2 is 45. And 3 is 45 and 4 is 45. Those are given. Flow proofs, you write your statement in the box, you write Y underneath. So then we said angle 1 plus angle 2 is 90. 3 plus 4 is 90, and that's the angle addition postulate. Remember when we learned the postulate that you are allowed to add up angles. So that's why we were allowed to add those up and say they're 90. Then we said angle ABC is 90, and angle BCD is 90, and we did that by substitution. Because 1 plus 2 is ABC, we substituted it in. Then we said ABC is a right angle and BCD is a right angle because that's the definition of right angle, is it equals 90 degrees. Okay, then we said BA is perpendicular to BC because right angles by definition are perpendicular, and BC is perpendicular to BD by definition of right angle because it's a right angle. And then we can say BA is did I get that one right? Yeah, no, I wrote that down wrong. BA is parallel to CD because if two lines are perpendicular to the same line, they're both perpendicular to BC, then they are parallel. And that was the theorem we learned on one page back, Theorem 312. Alright, so there's a flow proof. Still not my favorite. My favorite's that one. Alright, you'll be doing some drawing on page 159, and that's it for geometry section 3.5. That wasn't so bad, was it? I think it's kind of interesting. Hope you do too. Math is fun.